Okay, I welcome you all for this class on module number 4, what we were discussing. In the previous class, we had already completed the construction and working principle of a DC generator, and we have also finished the EMF equation of a DC generator. Okay, so those are the two concepts that are there for a DC generator, and remaining concept, what we are going to cover is with respect to DC motors and synchronous generators. Okay, so if those topics are to be left, we are going to complete it soon, and that would complete the entire 5 modules for electrical engineering. Okay, basics of electrical engineering. Okay, so let me begin right now, and just after the completion also I'll be solving more number of problems, and a few of them as requested in the first half, that is module number 1 and a bit of module number 2. I'll be covering it, and I'll be solving more number of problems with the recorded versions, and I'll share the link to you. Okay, so completing the portions doesn't mean that the classes are over. More number of problems will be solved such that you will not have any difficulty in facing the examination or the test. Okay, so the second CIE that would be held as per the calendar of events, that is from 13th, 14th, 15th, that is there as of now. Okay, and we have the quiz. Okay, so the quiz dates are already announced in the group, so you have to be ready with the quiz. Module 3 will be there for the quiz. I want you to prepare well, and you have to see to it that all the questions that is asked. Okay, so it is on 8th. Okay, so 8th July. So it would be from 5 p.m. to 5:15 p.m. what the timings was there previously. Okay, so see to it that you are not going to waste time. Start preparing. Okay, and we'll see to it that all the portions are completed within time, and you will be getting time to go through the syllabus and also the content what we have covered. Okay, so completing the syllabus is one part, but it is you people who are going to write the test or the examination. Okay, and you have to understand the concepts which are being taught. Okay, because most of the concepts are relatively there in your elements of mechanical engineering, like motors or generators. You would have seen it. Okay, next you have the design of it in the upcoming semesters. Okay, so once you get into the branch, you have to understand what is its working principle, what are the different types of motors and everything. Okay, so without that, it would be really difficult for you to understand the concepts that are taught to you in the higher semesters. Okay, your fundamentals has to be right. All right, so let us not waste time in such things again. Okay, so I want every one of you to attend the classes regularly. I can see only 22 are there, so see to it that you are attending the classes regularly. Okay, fine. So without any delay right now, let me move on to the next topic, that is DC motors. Okay, so in DC motors, we are going to cover the topic such as principles of operation of a DC motor. Next, we got the torque equation of a DC motor. Next, we have got the types of DC motors that are there. Next, after the types of DC motors, we'll discuss the characteristics. Okay, depending on the characteristics, a certain application is to be like a motor has to be used for a certain application, and then you have to think about the applications of DC motors. Okay, so all those concepts along with certain numerical problems, I'll be covering it up in this part of the section, that is DC motors. Okay, so let us begin right now. As told in the earlier classes, that is DC motors. Okay, the construction wise, it is one and the same, and you will be having the DC generator and the DC motor which is there. So it is quite one and the same. Okay, so it is quite one and the same construction wise. Okay, I'm very much clear here. Construction wise, the DC motor and the DC generator is one and the same. Now, how do you define a motor? Can anyone tell me? Can anyone unmute themselves and they can tell me how do you define a motor?
It is a device which converts electrical energy into mechanical energy.
Yeah, very good, Bhavani. Yes. So the fundamental definition is one thing where you have the conversion being done from, that is the input and the output, right? So that is what you generally see in the principle of operation of a DC generator. You have a electromechanical conversion device. Okay. So you interchange it, it will become a generator. And then if you do the vice versa, that is the input as electrical and the output as mechanical in nature. Okay. So that is where you will be having the source as electrical and the load as mechanical, and you call this electromechanical energy conversion device as a motor. Okay, so you have an electrical energy that is DC in nature, and you have the output which is said to be a mechanical in nature, and then you will be having a pulley or any other load which is connected, so such that it drives based on the mechanical energy that is available to you. Okay, so that is the reason why it is called as an electromechanical energy conversion device. Okay, so that is what I wanted to show here. So this is a simple diagrammatic approach that we have got. Okay, so if I want to talk about the introduction aspects here, so what is the first thing that I need to keep in mind? That is the industries there, okay, or any other application which reduces the work. Okay, so the motor is having an output of mechanical in nature. I need to have the mechanical energy that is available. I need to use it for an application in such a way that our work is being reduced. Okay, so that is the main intention of using a motor or using a generator, so which has a particular application. Okay, so if an application is not required, there is no need of having such motors. Okay, so you want to have a motor driven vehicle. Okay, so there is a pedal operated vehicle. Okay, so in mechanical terms, if I want to say, I'll be having the pedal operated, that is based on the pedal conversion, and you have the motion of cycle or a vehicle there. Okay, so that is by pedal. Okay, so you call the term as moped. Okay, what it means? Motor pedal. So along with the motor, okay, you will be having the pedal arrangement that is there. So you can pedal it and you can move from place A to place B. Okay, so now if I have a motor, I'll be having less mechanical energy. Okay, I'll be having the less thing or less energy has to be spent in moving from place A to place B, or if I want to finish the work to be done. Okay, so I'll take less time. Okay, so that is the reason. If I say, like, if I want to have a cutter, grass cutter, DC motor, okay, I use a DC motor and I just make the like a cut which is there in the garden. Okay, so grass cutter. Okay, something like that would be there, right? So any application which reduces the time. Okay, so I need it, or most of the mechanical movement, if I want to make it, it would be a motor then. Okay, so why preferably DC motors? Okay, so why preferably DC motors? You will be having the simple construction and its cost is less, and most important thing is its maintenance. Okay, so when you come to the AC motors, generally you have developments going on in AC motors also. It is right now available in the market. So if I want to use it on like for a year or two, definitely I'll be preferring it for, I mean, the lower time. Definitely I'll be going for a DC motor. Okay, so now if I want to have a mechanical movement, as I told you, it has been accomplished by the electric motor. Okay, so electric motor on a wide range, on a wide spectrum, if I want to talk about it. So this electric motor is certainly used in each and every day's life. Okay, so wherever you come across. Okay, so starting from your bike, at the college level. Okay, so anywhere if you want to use it, or at the industries in case of large motor applications or electric trains. Okay, So most of the times I'll be using the electric motors. Okay. So now I have told you about the wide range. I'll be having the small motors, medium motors, and also the large motors. Okay. So small motors, or generally I call it as fractional motors, or I can certainly say it as low power consuming motors. Okay. And the next one, which is large motor applications, I call it as large power consuming or power rating. Okay. So you say it as 100 kilowatt. If you imagine a 100 kilowatt motor, so you will be having a overall size of the machine to be increased. Okay. That is the reason why you say it as a large motor, certainly used in electric trains, hoist, lift, if you have seen it. So, and metal rolling mills, milling mills. Okay. So if you come across any building company, so you will be having a large motor that is already being placed. Okay. So in case of small motor applications, a trimmer or an automobile or a robot or a hand powered tool. I mean, as a mechanical engineers, you will be having the hand powered tools which you generally use it. Okay. Or food blenders or mixers. Okay. So those are said to be the small motor applications. Okay. So either you take a small motor application or a large motor application, the principle of operation would remain the same. Okay. The principle of operation would remain the same, and there will be a change in the type of the motor which is there. Okay. So nowadays you see that in medical fields also, you'll be having micro machinery medical equipments that are there. Okay. So micro machinery medical equipments that are there. So in most of the biomedical applications or small machines that are generally used for surgical purpose, you will be finding micro machinery in the medicinal field also. Okay. So you find any field, you will be having DC motors that are generally used. Okay. So now this is a simple diagrammatic approach that is that I'll be sharing a few animation videos also in your group that would make the understanding better. So I have a simple magnets and also a simple loop that is there, and I have the supply. Okay. If you see it quite clearly, you have the electric current which is supplied through the external commutator. So commutator and the split ring arrangement, what you see here. So this is the entire arrangement where the conversion is being done from DC to AC. Okay. So DC to AC. So now it is inverted. Okay. So now it is inverted where the supply is DC in nature. So this makes the conductor to rotate. Okay. So what you are seeing here, the force is applied on it, and you will be having the current which is responsible for the production of the force, and you have the length of the armature conductor. So we call this as the armature of the motor or armature system in if most of the conductors are placed, and which is responsible for its movement is the production of the magnetic field which is there. Okay. So B is magnetic flux density, and overall if you see near the motor, it is the magnetic field that is present there. Okay. So you have F is equal to I, that is the current, L, which is the length of the conductor or the armature conductor that are there. Okay. And next you have the B, that is the magnetic flux density. Okay. So all are responsible for the production of the force, and this force will be acting on the conductors. Okay. So that is the reason why we call it as the force or the Lorentz force, which is responsible where the current carrying conductor is placed in a magnetic field which experiences a force there. Okay. So you have a conversion from the electrical, which is the source in nature, and you will be having the conversion to the mechanical output. Okay. So output is always mechanical in nature. Okay. So this is a simple way where the Fleming's left hand rule gives the direction of the Lorentz force, which is generally the force that is acting on the armature conductors. Okay. So if I want to talk about the principle of operation, I have the force as the main parameter that would be exerted on the coil, and it results in the interaction of the magnetic field and the electric current. Okay. Now, as I told you, you will be having the magnetic field that is being developed, and you have the magnetic flux density when two ends of the coil are connected across a DC volt, and you have a current flowing through it. Okay. So So once you have the force that is exerted on the coil, so it is having an interaction of magnetic field and the electric current. So the force on the two sides of the coil starts moving. So it is more or less like a cycle pedal. So once you step on one of the pedal and the other pedal comes up directly. So you have to keep moving. So in such a way that you will be having the force which is exerted on the coil, and the direction of the force is also dependent. Okay. So once you have several such coils that are wound on the rotor of the machine, we call it as the rotating part of a machine. So that is responsible for the rotation there. Okay. So this is how the principle of operation of a DC motor is dependent on. Okay. Any doubts up to this point? Anyone? You can unmute yourself and you can talk with me. Any doubts up to this point? You can talk with me right now. If you have any doubts regarding the principle of operation of a DC motor, you can let me know right now. Okay, so assuming that you don't have any doubts which is related to the principle of operation of a DC motor, let us move on to the next one, that is the significance of back EMF. Okay, so the significance of back EMF. Okay, very important concept. What I'm going to tell you right now, the significance of back EMF. So back EMF, okay, or we call it as counterclockwise EMF or counter EMF. Okay, so that is acting in the opposite direction to that of the applied voltage, applied DC voltage. Okay, so let us move right now in understanding the significance of back EMF. Okay, so when I say that as the armature is rotating or it is moving in nature, so this movement which is there will be responsible for the production of a voltage which has been set up in the armature winding, which is opposite to that of the applied voltage. Okay, so this opposing nature of the voltage which is responsible is called as the back EMF. Okay, so you can note down. You can note down. So armature starts its movement, and you have the armature winding that is responsible for the production of voltage. So this opposing voltage is called as the back EMF, or we call it as the counter EMF. Okay, so back EMF is also called as counter EMF. Okay, so now you have this back EMF which is proportional to the field. Okay, proportional to the field. When I talk about field, it is the field current or the flux which has been developed. Okay, so the back EMF will be directly related to the field, and it is also proportional to the speed of the armature. Okay, so this back EMF that has been produced will make the DC motor to act as a self-regulating machine. Okay, so underline. You will be making this DC motor to be acting as a self-regulating machine. Okay, so now depending on the back EMF, you will be having the armature current which is flowing in the circuit such that it is enough to drive the motor. Okay, so enough torque will be produced to drive the motor, and it takes the motor to draw the armature current which is sufficient enough to drive the motor. So that is sufficient torque needs to be developed to drive the motor. Okay, so once you have the armature current to be small, the back EMF will be directly, like, it will be equal to the applied voltage. Okay, so therefore the back EMF and armature current, so which is responsible for the production of the torque. Okay, so that is the reason why we call the back EMF to be responsible for making a DC motor to be a self-regulating machine, because it regulates the flow of armature current in the armature winding. Okay, so that is the reason. Very important question. Okay, so what is the significance of back EMF? Okay, so you might expect a question like that. Fine. So this is the significance of having a back EMF. So this is the equation for back EMF. Have you found this equation somewhere else? Have you found this equation somewhere else? Okay, have you found this equation, what you're seeing there on the screen? Have you found this equation somewhere else? Dinesh? Dinesh is not there? Okay. Chetan P?
Yes, sir.
Arthur? Yeah, have you found this equation somewhere else? Chetan?
Sir, no ideas.
Have you come across a generated EMF equation?
Sir,
What is the EMF equation of a generator? Abhinandan BS? Bhavani?
Yes, sir.
Yeah, have you come across this equation somewhere else?
Sir, it is same for generator equations.
Yeah, that is the reason. Okay. Yes, you are absolutely right. Why this equation, what I've mentioned here for the back EMF as the generated EMF is, so it is opposing the DC voltage. Okay. So it is responsible where the DC, when it is converted to AC there, so you have the generated EMF where it is equal to the back EMF in case of a DC motor. Okay. So that is the reason why the equation for the back EMF is given as the same equation of the generated EMF. Okay. So you know that the back EMF generated will be directly related to the flux and also the speed under the normal working conditions. Okay. So that is the reason for the back EMF, which is directly related to the flux and also the speed. Got it? Any doubts up to this point regarding the significance of back EMF? Any doubts, do let me know, because this is one of the important concept which is related in a DC motor. Okay, so that is the reason. As you can see, so you have the back EMF that is being produced. So this is a typical like the CAD model what I got there in the video. So you have the input that is DC in nature. Okay, so you have the back EMF which is being produced here. Okay, so this is the armature conductor and you have got the laminations being there, and later you have the plus and minus. Okay, so plus and minus represents a DC supply. So, and you got the split rings and the commutator and the brushes which are arranged. Okay. So, along with that, you will be having the back EMF which is there in the armature winding. Okay. So, that is the reason for it. Okay. So, back EMF will be opposing the generated EMF. Fine. Okay. So, if you have any doubts, do let me know. Okay. So, that is the significance of having the back EMF. Okay. So, any doubts up to this point regarding the significance of back EMF? Any doubts? Any doubts up to this point? Anyone? You can let me know. You can let me know right now if you have any doubts. Okay, anyone who is having any such doubts, you can let me know, or else we'll move on to the concept which we generally call it as the torque equation of a DC motor. Anything that you got in your mind regarding the working principle or the significance of back EMF, you can let me know right now. Okay, anything that you have got in your mind, anything that is there, you can let me know right now. Okay, so if you have anything, you can go through the video which I'll share it. And right now we will start with the torque equation of a DC motor. Okay, so very important derivation. Derive the torque equation or derive an expression for torque produced in a DC motor. Okay, derive the torque produced in a DC motor. Okay, so that will be the question. Okay, so now let me go with the fundamentals again. How do you define torque? How do you define torque? I think elements of mechanical engineering, you would have finished it. How do you define torque?
Sir, it is the force applied on an object to rotate that object.
Very good, Bhavani. So can I have few more answers from others too, such that this derivation won't be a bit of problem to you when you solve it or when you derive it in your classes or in the exams or test? Okay, any more answers? Feel free to express yourself regarding the subject. Any more answers? How do you define torque? A torque acting on a body, torque acting on a like any like circular object or something like that, anything or a point. How would you define it? Okay, so as Bhavani said right now, can you repeat the statement, Bhavani? I'll alter it a bit. Bhavani, can you repeat the statement, what you told right now?
Sir, it is the force applied on an object to rotate about its axis.
Okay, fine. So in numerical equation terms, I can say it as force into perpendicular distance. That is torque. Do you agree to that?
Yes, sir.
Do you agree to that?
Yes,
No,
sir.
if I'm wrong, you just let me know. No problem. We can have our discussion. So I said that the force into perpendicular distance and not generally any distance there. Okay. So now if you have the mechanical output which is generated, so you have a pulley arrangement and you have the rotational object there, right? So now the torque which is responsible, as I told you, it is generally the force which is acting on the armature conductor. Okay. So the force which is there and also the distance on the conductors that is there from the central, what we take generally. So that is taken as the perpendicular distance. Okay, so it is assumed to be cylindrical in nature. So you have the conductors which are being wound will be having a cylindrical area of cross section. Okay, so if I take the force which is acting on it and the perpendicular distance, I'll be getting the torque. Okay, so this torque is responsible for the rotation. Okay, and you have a speed. So torque and speed are inversely related to each other always. Okay, keep this in mind as a mechanical engineer. Torque and speed are the mechanical parameters and they are inversely related to each other. Okay, so let us derive right now the torque expression of a DC motor. Okay, so now I told you the torque which is responsible, we call it as TA, that is the torque produced in the armature system in a DC motor. Okay, so after the torque which is being produced, you have a speed at which the armature starts rotating and it is expressed in RPM. Can anyone tell me what is RPM full form?
Rotation per minute.
Revolution per minute.
Yes, Bhavani is right. Bhavani is right. So it is revolutions per minute because it is revolving around a fixed path. Oh, okay, so you are taking it. It is more or less like a rotation of Earth around the Sun in an elliptical orbit. Okay, sorry, revolution of Earth around the Sun. Okay, so rotation will be about its axis and revolution will be around a fixed path which is taken from the center. Okay, so if I keep any object in the center and if I have a path which is being traced around that central fixed object, I call it as a revolution. Okay, so I say n will be the speed at which the armature is rotating, expressed in RPM. Okay, and how are you going to write the velocity? Okay, so speed and velocity are two different terms. So speed is one thing where you move at a certain rate, and you have velocity which is displacement by time, and speed is given as distance by time. Okay, so displacement is one thing which is the shortest distance that is to be followed. Okay, so the angular velocity is given by 2 pi n divided by 60. Okay, so why it is 2 pi n by 60? So you have the angular nature that is there. So overall you will be having get traced by 360 degree. It is mentioned as 2 pi n by 60 and it is expressed as omega. Omega equals 2 pi n divided by 60 radians per second. Okay, so now you want to find out what is the mechanical power developed and you want to find out what is its electrical equivalent. Okay, so the mechanical power developed is given by PA. Okay, that will be equal to TA into omega. Okay, power developed in the armature is given by PA equals TA into omega. So I take it as equation 1 and I want to find out its electrical equivalent. Okay, so what is its electrical equivalent? So PA, that will be equal to EB into IA. Okay, so EB is given as back EMF and IA is given as the armature current. Okay, so what is the equation for EB? What we told right now? What is the equation for AB? Back EMF. What is the equation for back EMF? EB equals
P5Zn by 60A.
Very good, Abhinandan. Very good. So I can write it as P5Zn divided by 60 into A. Okay. So I can equate both the electrical power equivalent and also the mechanical power because the output is mechanical. I am expressing this mechanical power in terms of the electrical terms. Okay. So what do? I equate equation 1 and 2. Okay. And I substitute the value of EB. Okay. So I substitute the value of EB. So what will I get? I'll be getting the equation TA, which will be equal to 1 divided by 2 pi phi z into IA into P by A. Okay. Phi z into IA into P by A. Okay. So that is what I'm going to get as the armature torque equation. Okay. So that is what I'm going to get it. Fine. So any doubts up to this point regarding the derivation? So we are taking the electrical equivalent of the mechanical power developed. Okay, mechanical power developed is EB into IA and electrical power developed. Okay, this is the electrical power developed, and this is the mechanical power developed in the armature. Okay, so that is what we call, and we get the armature torque to be equal to 1 divided by 2 pi phi z into Ia into P divided by A. Okay, so now what are the constants that you see in the equation here? What are the constants that you see? Hemant PB, can you tell me what are the constants that you see in the equation? Yeah, Hemant PB, are you there? What are the constants that you see here? Okay, TA, what are the constants? Poles are fixed, number of parallel paths are fixed, the Z is fixed. Okay, so all these things are said to be a constants. Okay, Z, P, and A, and the armature torque is directly proportional to phi into A. Okay, so you have the output which is produced at the shaft of the machine. Okay, so that torque which is responsible, where it is the mechanical energy which is generated at the shaft of the machine, the torque which is developed at the shaft of the machine is called as the shaft torque. Okay, so TSH, that is the shaft torque. Okay, so you have the power output, you get it as 2 pi n by 60 into TSH. Okay, so which is expressed in watts. Okay, so you get it as the torque and the output produced at the shaft of the machine. Okay, so that is what you need to remember. So the power output will be at the shaft of the machine. Okay, so this is the torque equation of a DC motor. Okay, torque equation of a DC motor, derive the armature torque of a DC motor and express the power output in shaft torque. Okay, up to this point you need to write the derivation. Okay, so any doubts up to this point now? Any doubts up to this point, anyone?